think we started talking about that clustering concept last time, right? Uh, I think I discussed a little bit about that, but we did not finish talking about that all the calculations here, right? So we will refresh our memory on that, and we will continue from there. So we started this concept of this clustering, and then so I can finish up this discussion today, and then I can go into the concept of the simulations, and so I will start the simulations concept as well, right? So okay, so now first let's start talking about this on the concept of the clustering. So we identify this topic last time. So what are the our main goals in terms of this clustering? So we identify that we have the our multivariate data, and so I think I discussed about that in terms of the multivariate data set, right? So once you have the your multivariate data set as the say x1, x2 up to xn, right? So once you have the set of data like that, then we have that our all the observations, we can collect them into a matrix like that. The x1, x2, 1, 3, 1, and so on, and so on. Uh, so I put k here, and so we have the k number of variables, and then I have the n number of observations there. Uh, 2n and k number of observations like that. So with that, the once you have your data set, so we discuss about that. Like if you we can group them in terms of their variables, as well as you can group them in terms of their observations. So these are their observations, right? Observations, and these are their variables, right? So we have their observations and variables. So we can group in either ways, right? So grouping in terms of variables and grouping in terms of their observations. And we talk about that grouping in terms of the variables is calling the factor analysis. So that's the variables we normally we can call them as factors as well, right? So we can find in the properties of the vectors. That's called vector analysis. And then grouping in terms of their observations. So we discuss that as the and the grouping them as the cluster. So that there is our cluster analysis. So we try to find out different clusters among their observations, right? So now if you look at that, like the taking two variables at a time, right? Taking just say x1 and x2, right? So then once you plot them, right? Sometimes you might see that like they might have certain properties like that, right? So then you can see they can put into two groups like that and so on. And so we can find out certain uh, grouping of set of observations and another grouping of another set of observations and so on. And so it can be like several number of groupings we can have. So we can identify them as the different number of clusters we can have, right? So then we discussed that like I think like the in terms of these clusters. So as the number of variables are increasing, we cannot visualize it. So then we don't have much idea about the identifying what are the suitable number of clusters we can have. So in that case, of course, we are in trouble of deciding how many clusters we have to go, right? But then in that case, of course, we have some idea that in terms of the clusters, we uh, now we are trying to follow that like different approaches there. So we discussed that like we can go with the hierarchical clustering as well as the non-hierarchical clustering. So if you go with the hierarchical clustering, then that will give you some idea about how many clusters we can have and so on. But if you look at the non-hierarchical clustering, that is the k-mean clustering that we are going to talk about here. So in that case, we have to decide that the either we can go with like the two clusters or three clusters and so on, and we have to keep on doing it. So it is kind of like we are trying to do some iterative work, and we try to see whether we can find out the suitable clusters. So then in terms of like how we define our clusters, so it's going to be the to describe our cluster, we like to find out a suitable place. So that is the suitable place is the center. So for each cluster, you can identify a center. So that center might not be an observation. So just a particular point that we like to inform, right? And then we like to say that. So with that center, the set of observations will considered as a one cluster. And with this center, this set of observations will consider it as another cluster and so on. And so that's how we can divide them into the two groups like that. So then in terms of like once you're dividing them into the groupings like that, the our target is to now the we need to define certain property to identify. So so in that case, of course, now we can go with the distance concept. So we like to measure a distance. So now, as we are looking at that, like these are observations, right? So we have that bunch of observations, right? So like the in terms of like if I, for an example, now if I give you a question, right? So as a if you want to analyze about a company or whatever, right? So that there's some opinion of the uh, your customers or like or your workers or whatever, right? So you can decide a questionnaire there. So once you have the questionnaire, then you have a bunch of questions there. So in your question, it is not just one question, right? So once you create a questionnaire, there will be like 10 or 20 or 30 questions there, right? So usually we like to have like reasonable amount of questions there, right? So it should not be too large, right? So like so usually we are not going to give a questionnaire with 100 questions, and so but whenever you are preparing a questionnaire, something like around 30 questions will be enough, right? So then people can easily answer them within 5 or 10 minutes, right? So whenever you are planning a questionnaire, so you plan to have like something to like 20 to 30 questions there. So that those 20 to 30 questions are the variables that we have, right? So that's you have that 20 to 30 questions. That's going to be the k will be either 20 or 30. So they have 20 to 30 variables are there. And then you are giving that to each and every the person in your in your group of customers, right? So you can of course right, we are selecting set of customers as random sample, and then you're going to give to them, right? So then their responses are recorded like that. So that's the each observation. So then now in terms of like clustering these observations and so on, and so we like to the measure how close these observations are, right? So now if you look at the two dimension, if you have only two variables here, right? So then if you look at the two dimension, then you can find out if you take two observations, you can find out how close they, right? So, and like that now, if you find these two observations, you can see they're having much larger distance. So like that, now between each and every observation, you can measure their distance. So this distance, these are the distances we can call. So these are called the Euclidean distance. Okay, so that's our regular word that we are using as whenever you are measuring the distance in the 3 dimension, right? So now if you have that like 2 points like that, the x1 1, x2 1, and so on, right? So then x 1 2, x 2 2, the 3 2, and so on, right? Then if you have say something like that, two observations like that, then the distance between x1 and x2, right? So if you take the two variables x1 and x2, right? Then distance between the two observations, right? So that is so it is not the x1 and x2. I can define as the observation 1 and observation 2, right? Between observation 1 and observation 2, right? So between the two observations, right? So that can be like these two, or whatever, right? Any two observations, and we can measure the distance as the the Euclidean distance. We define it as our distance formula. That is the x11 minus x12 square, and x21 minus x22 square, and so on, x k1 minus x k2 square, and the entire square root. So that's how we can measure the distance between the two observations, right? So like that, now whenever you find out that once you have a set of data set like this, right? So then if you have the n observations, then we can find out the n by n number of distances, right? So between the first one and second one, first one and third one, and so on, right? And first one and nth one, right? So we can find out all these distances. Then we can find out actually that we can represent them as a distance matrix as well. So we can put all these distances as a distance matrix as well, right? So that is so we can put them into a matrix like that. So that is observation 1, observation 2, up to observation n. And these are our distances. So d11, d12, and so on. And so we can find out all these distances like that, right? So that we can gather all these distances as a matrix like that. Okay, so we need these distances. So that is the Euclidean the distance that's named after that mathematician Euclidean, right? So Euclid, right? The mathematician is Euclid, right? So now the in terms of like the distance measurements, now this is like that one type of measurement we can have, of course. The in terms of the other methods, there are several other methods we can use as well. Give me a second. Okay, so yeah, right. So I just check whether it is recording. So it is recording, right? So so that is the idea of that. Like we can have our Euclidean distance defined like that. And now in terms of like whenever you are thinking about like other approaches there, Now, when you're measuring the distance, there are other methods of defining the distance as well. So that's like mathematical. There are several other techniques you can apply as well. So the in some cases, sometimes people are using those measurements as well. So it's the always you have freedom to use different distance measurements as well, right? So, but commonly we are using our Euclidean distance, right? So if you are using like different distance measurements, then you have to use the correct formulas for those, right? So only change is that, like, so if you are using a different distance measurement, then you have to use that formula. Okay, so that's the concept of the distance. So now, once you're looking at these distances, right? So you can identify now. Initially, now we now we, we can take all the distances in the, like a matrix like this, right? And then like so you can see that like this matrix is kind of like a symmetric one, right? So that's this number will be similar to this one, right? So that distance between first one and second one same as the second one and first one, right? So that's right. So these of diagonal ones, so these are similar, right? So they are like, therefore we need to worry about only one half of that one, right? So now, whenever like you're measuring that, when you're looking at all these distances, so then uh, we can apply our hierarchical clustering technique based on those distances. So that's kind of like another approach we can have. But then the other than that, if you look at our Riemann clustering technique, so in that case, of course, now we need to define that how many centers we are using, right? So how many clusters we are having, right? So that means we have to have the what are the centers that we can have. And then what we'll do is that we are going to measure the distances between the center. For each and every observation, and we like to measure the distance between that each and every observation and their center, right? And then similarly, we measure that all the observations to that center. And so all these observations, we can measure them to each of these centers. And so if you have like several centers, and so that for each center, we have to measure their distances, right? So then once you look at that, now if you take a particular observation, right? And if you measure the distance from that point to the others, the two centers. Now, in this case, now we have two centers, right? If you have three, then we can measure three distances from that point to the centers, right? Then by looking at that value, you can see where that the smallest one out of them, that should be the best and the center to represent that point, right? So once you are taking them, right? So if you're taking a particular point and you see the distance is the smallest to a particular center, then you can decide that point should be belong to that center, right? So like that, you can compare them, taking each and every point and measure its distance to each center, right? And once you measure that, then the if you can notice that the one of them is the smallest, then so you can decide that point should belong to that particular center or that particular cluster, right? So like that, now we can identify a set of points, right? And then we can say that so those will belong to those set of points will belong to one center. And then the another set of points will belong to another center, and so on. And so we can measure that for entire our data set and decide the each and every observation, how can we group them into the two groups, or like if you have two or three groups, right? So how do you put them into the each group, right? So we can decide on that. Okay, but then now after you do that, then now we have to repeat this several times. So then what we can do is like now our approach will become now initially write it over here. So the let's say that now if you have the two dimension, right? So we have a bunch of points over here and another set of points over here, right? So I have the all the data set like that. Now, once we look at it, now if you can visualize it, we know that here it should be the center and here it should be the center. But if you cannot visualize it, then you just have to randomly pick 2 points as our centers. So maybe I can take this one as the center and then this one as the center. So we don't know, right? So just I'm randomly selecting 2 points, right? So then if I measure all the distances from this point, right? And then from this point, then you can notice that some of these points will go into one cluster and the others will go into the other cluster. So it may be not the perfect arrangement. And so I'm just putting them into the two clusters like that. So once I go through that entire data set and decide that set of points, so for an example, if I draw it something like this, you will see. So say I have some points goes like that, right? And then another set of points might be going like that, right? Then I select that 2 points as the one here and one here. So then if I decide that looking at some points, right, then all these points will go into one center, right? And all these points might go to the other, right? So it depends, right? So now you can see that some might be cut like that as well, right? So there can be like some overlapping, something like that, right? So then you can take all these points here, right? And then average them out and you can find a center for them. And so to represent all these points here. And then to represent all these points here, you can find another center here. So I can change the center, right? So I can, in the next iteration, I can change the center and I can repeat this, right? So every time I change the center and then check whether that, what are the points inside. And then once you repeat it several times, right? So initially your centers are going to be like that, but after repeating it several times, you will get center over here and center over here. So your centers are moving, right? So there is no one coming to here. So you just going through these several iterations, you are moving your centers and then arranging them into the correct point. So it's kind of like each iteration you are doing some correction and then eventually you are approaching to the correct value. So then, of course, now since we don't know like whether that say 2 centers are okay or 3 centers, right? So like whether to have the 2 clusters or 3 clusters or 4 clusters and so on. And so therefore, like sometimes if you try this with the 2 clusters and but if you're not converging, right, so that you're not approaching to a certain number, then that means there might be like the number of centers may not be the correct. So you can repeat it again. So you can repeat it as the by changing number of clusters. So like, and then also it depends on your starting point as well. So might be like based on your two starting points, they might be having a different approach. So therefore you can change your starting point as well. So by doing that, you can repeat it several times and eventually your target is to converge to a certain number. Okay. So so that's going to be our approach here. So let's see that how we can perform that in our Excel, right? So if I do the calculation in Excel, right? So now And imagine now I have the data set as the three variables, right? So we are having a simple situation, right? So having that only three variables, right? So then I am just putting that customer ID here, right? So I have altogether 200 observations here, right? So I just um, repeated that as the k n equal to 100 here, and then I'm using that the random number function here, right? In terms of the Excel, I have the random number generation. So the every time when you use the random function, right? So they are providing value between 0 and 1, right? But I want to have one between the 1 and 200, right? So therefore I have to multiply that by the 200, and then so I had to round it up, right? So that's why I'm saying that the round it up to the next nearest integer. So that's why I'm using this ceiling command here. So that ceiling command is to round it up, right? So if I'm getting something like the say 108.4, 108.5, something like that, then it goes to 190, right? So like that. So I can round it up into the two numbers there, right? And then I'm just taking those starting points. So the these are the now the two random numbers I have. So that means I'm going to look at the 109th observation and the 187th observation, right? So then, so by looking at our data set, right? So I need to identify that the uh, what are the observations we have representing that data set, right? So therefore, I can look at this using the VLOOKUP command, right? And then I look at that J3 value, and then I'm using this. I just label my data set as a table clustering 510, right? So then I think I mentioned that how we can get this uh, identified as a table, right? So just select the entire uh, table and then go to the format as a table, right? So then we will get a labeled your entire data set as a table, and then you can easily refer that one, right? So you can use that clustering 510 command here. So that's going to give you the entire data set, right? So then I'm saying that under that here, the yeah, which column that I need to focus on here, right? So that's I'm focusing on the column number 2, right? And then the range lookup. So we are not asking to do any range, right? So just looking at the particular observation. So that's why we are saying it as false, right? So that's how we can collect that our values the for the each observation. So just you can see that we have to change the column, right? So each and every observation. So by looking at our data set, we can decide the 2 points. We can identify the 2 points as the 60, 50, and 49, and then 33, 86, and 95 as the our 2 points that we are initially considering as the our centers. So we don't have much any idea about like where these 2 points are or whatever, right? So we just randomly take these 2 points as the our centers. Okay. And then once you identify these 2 points, then we can perform our first iteration. So let's consider the first iteration. So give me a second. Okay, so let's continue with uh, the iteration one, right? So now our target is to identify these two as our centers, and then we want to measure the distance between the each and every observation and the center. So I'm going to do this calculation here. So you can see that like that's kind of like a very lengthy calculation, right? But it's basically I'm using that our formula that I mentioned over here, right? So there is the distance formula we can have. So you can see taking the square root between the B2, C2 and D2. So that's the values here, right? In terms of the data set, right? B2, C2 and D2, and subtracting the K3, L3 and M3. And so that is K, L and M, right? So that's these three values, right? So then I can repeat that for all the other 200 observations. And then similarly, I can do the calculation between the each and every observation and the second center. So I can measure the distance between the 2 points. So basically, I have that the so once I look at I have the entire data set, right? So I assume that certain 2 points as their centers, right? And then I take each and every point and measure their distance between the centers. So, right? And once you do that, then you can see that if you take this observation here, then you can see it is much closer to this one than this one, right? And if you take this observation, you can see it is much closer to this one and then this one. So therefore, you can see that some observations you can put under the first cluster and some of them you can put under the second cluster, right? So like that, I can separate them into the two clusters. So so that is what I'm going to do over here using this match command, right? So I'm taking the minimum out of K9 to L9, right? So that is K9 to L9, right? So that's these two. So if you can have like the three or four, right? So if you're deciding to have the three or four the centers here, right? So then three or four clusters, then there will be three or four columns here, right? So then measuring the minimum between all of them, right? So and then we want to find out the minimum out of the two values, right? And then the so okay, so here that what I'm saying is that the lookup value means that so taking the minimum out of these two, right? So I take that the minimum out of those two, right? And then I'm asking that look at the array of that K9 to L9, right? And then take the observation value. So that is what I want to have here, right? So that's so matching type. I had to check on that, like why we put 0 for that matching type. So I think that is regarding that, looking at in terms of the rows, right? So if you put 1 there, I think it is looking in terms of columns, something like that, right? So so we are looking at that the taking minimum value, right? And then the K9 to L9, that is the looking at these two, and the matching means that we are taking the observation ID, right? So that is the whether it is cluster one or whether it is cluster two, right? So we are taking the minimum out of them, right? And then we are finding out whether it is the cluster one or whether it is cluster two, right? And we are putting that number there, right? So that is what we are trying to do there, right? So by checking at each one, right? And deciding which cluster it is. So you can see that now in this case now the majority of them are in the second one, and then others are in the first one, right? So you can see, uh, so I can separate them into the two clusters like that. So that's my first iteration, right? So I just the uh, go to each and every point and measure their distances, right? And then once you have that, this is the minimum value, right? So then I decide to put this to this cluster. So and I'm labeling in front of that. This observation belongs to the first cluster, and same as this one, and so on. And so they are depending on that. So we are labeling them whether it belongs to first cluster or whether it belongs to second cluster. Right. So now in this case I have two, right? So you can modify that to the if you have that the several if we go for three or four clusters, then modify this up to the three or four, right? So that you can increase that by the different the columns, the number of columns that you're looking at. So that's how we can perform that our initial iteration. So now these two centers may not be the perfect ones, right? So therefore, what I want to do is the now I want to measure that the uh, whether that the once I divide that these into these I decide the clusters, right? The now by taking these set of values, right? I like to measure what's going to be our new center. So now my the second iteration, right? So I can perform the second iteration here. So I can perform the second iteration here. So I want to take the averages. So now I can take that the okay. So now I have to do some modification here. So I'm labeling this 511, right? So that is so I can label this set of observations as a new table, right? So then I'm putting them as the table 511 here. And then this is my uh, initial data set, right? So that is 510, right? So that's the so I had to do those modifications. So that's the idea we have, right? So by I'm using now this the function as the average if. So I won't do the averaging, but I'm saying that using some if command here, right? So what I want to do is uh, look at the table 511, and there is this table here, and then I'm asking to look at the cluster number, right? So that is the cluster number column here, right? So that's in this table. They look at the cluster number column, right? And then the uh, and the criteria is that like checking whether the number is one or two, right? So if it is one, then the average our data set age column, right? So I want to have the average of that, right? So and then next one, the look at the cluster number column, and if it is two, perform the average of each column, right? And so on, right? So then each one you can see the annual income variable and then the spending score variable, right? So that's each variable, and you look at the column the, and do the averages of each of those columns. So then I have the new centers here. So these are going to be the new values for the centers. So by looking at these numbers, what can we see? So my initially, I take the 46 as my center for the age, right? But then it changes to 44.2. And then the income as 54 here, but it goes to 66 here, right? And this has 44, but changes to that 9.2. So like that, you can see some changes there, right? So, and this is 39 goes to 72, right? So that's a large change there. And 61 goes to 73 or 74, right? So that's the some observations you can see that having a larger difference, right? And some of them are close. So you can see that these are going to be now my new values, right? So with these new centers, again, I have to perform the same thing here, right? I can perform the same calculation what I have here. Okay. So that is my iteration number two, right? So I have the cluster number. So then what I'm doing is that I'm taking the difference between our data set B2, C2, and D2 and the QRNS, right? So this QRNS, these three columns, right? So I'm having the new centers there. So these are my distances, and then by checking the each value, then I can decide which the cluster they belong to, right? So here you can see the I can check which cluster they belong to. The majority of them goes to the second one, and the rest are going to be the first one. So, so that's one iteration, second iteration, right? And then I can do this third iteration, and so on. That you can perform several iterations there. So that's my going to be my third iteration. So and here that and these are stated 7 12, right? So I have to change that here. So I have to label that correct table value there. Okay. So like that, I can label that each. I can calculate that by checking the label there, right? Then if I look at that these values and compare them, now you can notice that this is 30 to 32, but then 67 goes to 50 and 71 goes to 49. And so you can see that street is changing, right? But here you can see like only the last one is changing, right? So there is 73.9 and 51. So, so after performing that, they are going into third iteration, still you can see some changes are there, right? So we can keep on doing that. So that's going to be the third iteration. Again, that you calculate the distances. Output. So this I just when I copy and paste it. So once I put dollar sign here, it is easy. So then I have the identifying the cluster. So that's the fourth iteration. At 13 minutes. So I have to change it to 13 here. Okay, so that's how we can keep on doing that. And now if you compare them, the so now you can see that like once you compare them like throughout here, so starting from 32 here, right, and goes to 31 and 31 and 32, right? So that means now age value is kind of like converged, right? So you can see it is getting closer, right? And here it is 40, 40 and 40, right? So it's always around 40, right? And then the other value is 86 is quite similar here. 76 and 78, right? But then it comes to 86, and then 85 and 79, and 83 and 87. So that's kind of like this is still kind of like slightly changing, right? And then the other one, 53 and 55. But then this is kind of like the 72 and 54. So it is around 50s, right? So you can see it is changing to 50s, right? And then this 43 and 42. There is 48 and 78, right? So therefore, like now you can see they are kind of like getting converged, right? So if you perform these iterations another 3 or 4 times, then you will see. So it is kind of like converging. So that's how we can perform this one for the having like if we decide to have the two clusters, right? So same thing you can do if you go for like three clusters as well, right? So this is the idea that if you go for the three clusters here, so if you go with the three clusters there, so you can decide to have the three values here, right? So I just copy and paste these three here. So, so So anyway, like these two numbers are changing. I was checking okay, I forgot to try. So that like this is equal to this one, right? So then it is okay. So I'd say that is equal to that one. So so I can decide to go with three clusters, then I can have these numbers there, and then I can do the calculations here for each center. So I can measure the distances. And then I can check the checking these and finding out the minimum out of them. And then find out whether it's the uh, coming from the first column or second column or third column. And then you can see the uh, how it is separated in the three clusters there. And then I can go with the averaging here. So yeah, that is my iteration one. So I can go with the average if I'm iteration one. And then my table as the clustering table, right? So that's my table name. So averaging the for the three values there, right? So then you can see this is 31 and then 32, 29 and 40 and then 31, 36, right? So you can see that some change is there. Then you can repeat this one, right? So then you can go with the, again, the calculation here. The distance calculation. So you have to perform three distance calculations here. And then again, by checking them, right, find the minimum out of them, right? So then finally, you can do the calculations again. The by labeling this as the iteration number 2, right? Then calculate the so by calculating the centers again, right? So you can see that they are again changing, right? So again, you can see that you have to keep on doing these calculations for several iterations, and you will find out the what are the suitable number of clusters and the what are the centers you can have. So you can repeat this like the 3 or 4 times, and you will get some idea about what are the clusters you can have. So now, of course, practically you can see that this calculation may not be that easy, right? So that is, and this type of calculation is kind of like time consuming, right? So this is a bit more work to do, right? So so therefore, like if you use the something like the R software and so on, and so then you can see these calculations going to be much more easy than that, right? So let me show you that R software as well, right? So give me a second. Mm, I will open the R software. Okay, I think it is not here. Let open this one first. So I'm getting this error because I'm having the older version. I think I mentioned that last time, right? So, so now this is going to be the R coding. So let me put this one down here a little bit. So the please give me a second. I will start this one. Okay, right. So let's discuss about that and the clustering concept using the R software, right? So let's now to work on this now, we can collect that. If you have a data set, of course, I think I mentioned that how you can uh, the get the data set like, so I think this is we discussed last time, right? So you can use the read.table or you can use read.csv formats, right? So we discuss about this, right? So that is reading the different data sets that we had, right? So similarly, you can read a data set if you have in a text file or CSV format, Excel file, right? So now for the simplicity, what I'm going to do is like uh, I'm using some inbuilt data set available there. So this is kind of like a very famous data set that we have, the iris data set, right? So I'm going to refer that this iris data set, right? And then I'm using only the first one to the fourth one, right? So I'm using the first column to the fourth column, right? So that I'm taking all the observations, right? So this command is indicating that use this entire iris data set and only take first four columns, column number one to column number four, right? And all the other the observations in that column, right? So this is, yeah, I'm having the data in the matrix form and I'm referring them and they use those four columns uh, as the my data set. Okay, so that's my entire data set. And so I'm creating a new data set out of that as the iris data, right? So that is taking the first four columns. Okay, so that means I have four variables there, right? So, and then in terms of this, these four variables, right? So then now either you can go with this scaling or not, right? Doesn't matter, right? So that scaling means that you are subtracting the mean and divide by the standard deviation, right? So that if you take entire column, then you can calculate the mean and variance of that column, right? And then you subtract the mean and divide by the standard deviation. So that's standardization we can do. So that scaling means that, so you can do that standardization. Okay. So it's the up to you, right? So whether you can do the scaling or you can continue without doing the scaling as well. It doesn't matter. So the reason that sometimes people like to do the scaling because now the data might be in different scales, of course, right? So that is, some might be measured in kilograms and some might be measured in grams and some might be measured in meters and then some might be millimeters. So they can have like different numbers and the ones they measured in different units like that. So then once you're comparing something like a variable measured in kilograms and another variable measured in millimeters. So these numbers might have like one might be having very small numbers and the other one might have very large numbers. So they might not be having in the same scale. So that's why people like to scale them as well. So that's why they are doing this scaling side. So sometimes it's better to do the scaling as well. And so that you are in the same field, like all the variables are in terms of the same units. Okay. So and then of course to run the k-mean clustering, right? So the so I'm using that the the k-means as my command here, right? So that will allow us to obtain the K, K-mean clustering. So that's the same thing that we discussed here, right? So basically they are taking the centers, right? So the now you can change the starting value as the 10th one or whatever, right? So that you can give some number here as the starting value, right? And then they take randomly three centers, so that I can change the number of centers, right? So I put three here, right? So that you can take the any starting values, and then you can repeat that iterations, and finally, so you're going to stop the iterations as you converge to the certain number, right? So that's the idea of that the k-mean model here. So let's run this and see. So, so I'm loading the iris data set, and I'm taking that first four columns and the scaling, and then I run the k-mean model. So now actually that, so it is automatically decided what are the centers, right? So then I can use this print command to look at the result here, right? So let's see the result here. So this is the my k-mean model. So, so I'm having three clusters, right? And then the first cluster I have 50 observations. Second one I have 47, and third one I have 53. So altogether 150 observations are there. So and I'm putting them into the three clusters like that, and then the centers having that the four variables there, right? So in the in each one, so the centers are given there. So three centers are given there like this. So this is the converged value, right? So that's so after it runs several iterations. I think they are not mentioning how many iterations there. So maybe like at least maybe 100 or the 150 or something like that, like larger number of iterations has to be run, right? So, and then in terms of all the 150 observations, right? So the just like that we put that the cluster number. So this is the cluster numbering that we can have for each one, right? So, and then they have some other measurements here, and we did not talk much about these actually, right? So how good the clustering and so on, right? So they are saying that between sum of squares divided by the total sum of squares, right? That ratio is kind of like 76.7%. And so we don't need to worry about this actually, right? So that's kind of indicating that how good your clustering is and so on. And these are the available components. You can look at them, right? So, so that's the idea of like doing the k-mean clustering, right? And then you know how what are the observations that you can have in each cluster, right? So, and these are like the same results we are getting, right? So that's printing this part and looking at the clusters, right? So that these are the commands, right? You can give these commands like that, right? So just to show you that, right? And then like this, getting this table is kind of like something we can do with this data set here, but practically you don't have this option actually. So what this table is indicating that now originally once they create this data set, they know that these are like the measurements they have from the flowers. So that the iris flowers they are measuring here, right? So they are having that four variables defined as the sepal length, sepal width, and then petal length and petal width, and so on. And so these are the in terms of the flower, right? So the measurements they have. So in terms of that, the iris flower, so that it might have like various categories, of course, right? The iris flower has several categories. So they are measuring from each category in these measurements. So they have like several other measurements as well. They have like several other variables, right? So we just have only four of them, right? So then by looking at only these four variables, right? How can we put them into the each cluster? So now initially once you measure them, so you have a particular the species name given to them, right? So because of that, we can do this tabling here, right? So if I run this table, you will see. So that's these Setosa, versicolor, and then virginica. So these are the three types. The uh, they are mentioning on that, right? So these are the three types. Then the in terms of that these measurements, so they have like each type they were measuring. Um, they were taken like 50 the flowers, and they measure these and so on, right? So then altogether they have 150 observations, right? But then like by looking at only that those four variables that we are collected, right? So once you separate them, this is how the clustering happens. So basically like the 11 of these and 36 of these goes to the second cluster. And then 39 of these and 14 of these goes to the third cluster. So that's kind of like having some mixture there, right? So then this first one is already separated. So no mixture on that one, but this has having some mixture there, right? So that means like, so we need several other measurements to put them into the correct clustering perfectly, right? So so that's just the practically now. If you like, whenever you are collecting the data, if you have some idea, then you can arrange them, right? So, but otherwise, so we don't have such a table always, right? So it depends on how you collect your data. Okay. So and this library factor extra, so that's kind of like the additional library that package that we have to install, right? And that will give us some plotting of our data. So just we'll run that one and see. So, so it's going to give us some plotting of the data. So this is kind of like now they're looking at using two dimensions here, right? And then plotting them, right? So now originally we have that four variables there, right? So by just taking them, combining two of them together and then other two of them together or something like that, right? So they are looking at the two dimension, and then the separations are going to be like that. So this cluster is clearly separated, but this one having some overlapping or something like that, right? So they are not perfectly identified. And in this, the bigger circle here and then bigger square and bigger triangle here, these are the centers identified on each cluster. Okay, so so that's the idea of this. The clustering technique we can apply in the R software. So they can see that like, so this is much faster, right? So we don't need to do much calculation like the previous one. So just have to read the data set and then use the command. Okay. So this is going to be much faster. So other than that, our the non-hierarchical clustering, that is the k-mean clustering that we have, right? And there's another technique we can apply. That is the hierarchical clustering. So let's see that like what is this idea of this hierarchical clustering. So let me first introduce you that one. So the so the idea of this. So let me introduce you this concept as well. So now once it comes to the hierarchical clustering, so unfortunately this is not available in Excel. So uh, I don't think we can perform this calculation in Excel actually, right? So this is kind of like again like some iterative calculation we can perform, but so this is much more like we have to go through the process several times, but it is not a numerical approximation. This kind of like directly identified, right? So the idea is that now we can have the our distances. Now I mentioned that once you take that entire data set, right? So from one observation, you can measure the distance from that one to the others, right? So like that, each observation up to the nth observation, so you can measure the distances. So I have the D11 and 21 and N1 and so on, right? And then K2 and 2 and then so I can take that all these distances and I can take that like this lower triangle here, and it's kind of like a triangle, right? And then we are looking at that lower numbers, right? And then the same as this one, right? So it's yeah, symmetric. So that's these two numbers are the same. Okay, so we can define that as they're symmetric. Okay, so once you take that the entire in that particular matrix, right? So then we can see that, right? So by looking at all these numbers, right, we, we can identify that which distance is the smallest, right? Or like there can be several observations that has the smallest number, right? So once you identify that several observations are having that smaller number, right? So that means, so those observations are the closest ones out of the entire data set, right? So you can see that like some values, right? So we can identify they are the closest ones in our data set. And once you are checking on that each and every observation. So there can be like two of them has the smallest number. So then you can take those two as a one cluster initially. If you have three of them having the same number, right? So then you can take those three as your first cluster. So it's depending on the smallest number you have, right? So either you take two of them or three, four, whatever, right? So you take that as your initial cluster. So then now as a diagram also we can draw that, right? So we can identify several observations, right? And you know that they are the closest. So we can group them together like that. And we know that the distance, so we can see that that level, right? So these are the two closest ones that we have, right? And then the by taking these two as a one cluster now, right? Now I can create this matrix again, right? So now for an example, if I draw some table here, right? So putting some numbers, say I have to here. So I can put some numbers, just I randomly put some numbers there. So then what I can see is that, so this is the smallest one. So that is the observation 1, 2, 3, 4, and 5, right? So therefore I can say, so that is the 1 and 3, right? So that means, so in terms of observations 1 and 3, right? So I know that they are the closest together, right? So with this height of 1. Okay, so now I can take that observation 1 and 2, 1 and 3 as a one cluster, right? And then I have the 2, 4, and 5, right? So I have the rest. So then if you look at that, the 1 and 3, and then 2, 4, and 5, right? So then if you look at that, uh, okay, so I don't have these numbers. So those are actually zero, right? So we don't have that. In those numbers, distance between first one and first one, that is zero, right? So these are zeros. So I just need to look at this set here, right? So the so these are going to be zero anyway, right? So these values are not going to be there. So then if I look at this set here, so from this new cluster to the other observations, so I have to measure that distance. And the other numbers are there, and so that you can extract directly from here, right? So from 2 to 4, right? So that is 6, and so that's there, right? And then 2 to 5, that is 2, right? And then 3 to 4, sorry, 4 to 5, right? So 4 to 5, that is 2, right? So that's already there, right? So, but then if you look at and 1 and 3, and then 2, 4, and 5, right? So then these values we have to check, right? So then, of course, now you can see that, right? By taking that 1 and 3 as a one cluster, right? So that means we are taking this value and this value and this value, right? So, and then 3, this one and this one, right? So we have to check on these numbers and decide on which one I should go here, right? So that's kind of like the calculation we can follow, right? So if you look at these numbers here, right? So what can we say? What we can put over here? So now in that case, now to decide on these values, we have several approaches, of course. Now that is the idea of that our linkage here, that method, right? The linkage method. So that's called the linking those, right? So how we can link them. So there are several methods as the complete linkage, and then we have the single linkage, and then the average linkage. The average linkage, right? So there are like the different methods that we can follow, right? So so depending on that, then we can see we can put different numbers here, right? So the single linkage means that we are taking the minimum out of the two, right? So then the two, you can see 2 to 1 and 2 to 3, right? So then that is the 2 to 1, right? So 2 to 1 and then 2 to 3, right? So we are looking at these two numbers, right? And the minimum is going to be 3 anyway, right? So you can see that's 3, right? And then the 4 to 1 and 4 to 3, 4 to 1 and 4 to 3. So looking at these two, then you can take the minimum, that is 4, right? And then the 5 to 1 and 5 to 3, 5 to 3. So you can take these two numbers and take the minimum, right? So then that is the single linkage situation. So like that, you can keep on doing this, right? By using the single linkage technique, right? And so that's the idea of that. You're finding out the new distances here. And then by looking at this again, now you can see that minimum is this one here, right? 2. So that means the now you can put this 2, 4, and 5 together. So it's now basically now in this case now it is the 2, 4, 5 is kind of now new cluster. So therefore we don't need to do any other clustering, right? So then we have that 2, 4, and 5 goes under that height of 2. So they are in one cluster, right? It's kind of like two clusters are going to be like that, right? If you're using single linkage, right? And then complete linkage means taking the maximum out of them, right? So then this is 3, and this is 5 and this is 6, right? So then again we are taking the minimum, so that means the again the same clustering, right? And the average means taking the average of those two. And so like that, the we can define that different by using the different the linkages, right? So we can do the clustering, and then we can see we are getting some diagram like that. So we can create a diagram like this. So that diagram is called the dendrogram, right? So once you look at the dendrogram, then that will give you some idea about the our how many clusters we can have. So let's run this and see, right? So just in terms of the hierarchical clustering techniques, right? So first what we do is like we are creating the distance matrix. So using the iris scale data and using the Euclidean distance, right? So I'm creating the distance matrix, and if I just plot them, right, you can see that very large matrix, you can see 150 by 150, right? So that's yeah, I have got all the observations like that, right? So I'm just plotting it and see, right? So, and then I can use that hierarchical clustering H cluster, right? So that is the hierarchical clustering technique. And I'm putting my distance matrix there and asking the method. So we can put any name here at either complete, single, or average, right? So if I run that one, then of course I'm getting some result, right? But it is not visualizing any the output here. So to visualize the output, I can use this plot command. So using that HC model here, and then labeling them using the species of iris, right? And then put in some name here, right? So I'm asking to do the plotting. So that is going to give us the dendrogram. So that is the diagram that we are looking at. So you can see the diagram here, right? So let me look at this diagram. So that gives us the idea of that our clustering, how it is happening, right? So now, of course, now these names normally not going to be appearing, right? So, but you can put the observation number here. And so you can put the observation number down here, right? And what does this indicate is that if you cut down over here, and if you cut this tree from here, so then you fall down into two branches. So that means two clusters. And if you cut this tree from here, then you're going to fall down into three clusters, right? And if you cut this tree somewhere here, and somewhere in the middle like this, so then how many? One, two, three, four, and five clusters. So like that, you can decide what height you want to cut. Then you can see how many clusters you can have. So you can decide to go with like a two clusters or three clusters or four clusters, right? So depending on that, what height you like to cut. So that will give us some idea like how many clusters you can have there and so on. So now once you're measuring them, of course, another thing you can identify is that now the gap between these clusters. So you can see that like with the height of 4 here, right, up to the height of 4, right? So these are kind of like closer to each other, right? But then here that you can see big gaps are there. So that means like cutting down somewhere here is better. That means having 1, 2, and 3 clusters, right? So that's kind of like the idea of that we have the 3 clusters here, right? So that's kind of like the idea that we can have in terms of that having 3 clusters. The so let's run this command. I forgot what it is. Okay, so this is now the this command is to just take that the output here, right, and ask him to divide them into 3 clusters here. And so that cut the this is like the Q tree, right? So it's cut in the tree, right? So it's the indication, right? So that means you ask them to cut them into three clusters, and then you're looking at the data as the table that we decided earlier, right? So you can see how they separated like that. So now that is from the complete linkage, right? And we can perform the same thing with the single linkage. So there is the plot here. So in that case, now you can see this is like one observation is identified as a separate cluster. So this might be some maybe like some outlier or like some unusual thing happens here, right? So therefore, like one way observation usually goes under one cluster, but then you can divide them into the three clusters like that as well, right? So that single linkage may not be perfect on that case. So if you divide them into two clusters, you can see how it is happening here. And if you divide that into three clusters here again, let's see what happens. So you can see that like the second cluster only one observation. And so that's kind of like unusual thing happens. So okay, so this is now I'm recording that my same observations that I had earlier, right? So let's record them. I'm reading that same observations I used in Excel, right? And I can apply the k-mean model there, and I can go for four centers or whatever, right? So you can change that, right? So that is the information we have with the four centers, and these are the numbers we can have: age, income, and score, and so different values we can have. If you go for the four centers, right? So you can change this to two centers and see. If you go for the two centers, then these are the averages, right? So remember that in Excel, right? So we convert something like 30 here, right? So that's this is converts to 28.9 and so on, right? And you can look at the plot here as well. If you divide them into two clusters here, right, you can see some overlapping is there. And then if you look at the hierarchical clustering on that, the dendrogram you can have like this. So you can see that by looking at the dendrogram, you can decide that what height you like to have there. So if you divide somewhere here, then you can have the two clusters, and if you have somewhere here, then this one, two, and three clusters, right? So you can decide to have how many clusters you need. So this is now in terms of using the average linkage methods, and you can try the other three methods as well. So that's basically the indication of how we can perform this clustering, right? So I'm just telling you that like in terms of when you're performing the clustering, so we can go with that the different approaches like that. So with that, then I can end up the discussion on the clustering techniques, and I'm not going to go into the factoring because now in terms of the R software, sorry, in terms of Excel software, the factoring is not available, right? So I had to use some R software or some other, right? So therefore, I will not going to introduce you that factor analysis concept. So now with that, then I can go into the next topic, that is the simulations. So I like to uh, go into this calculation here. So before going into that, let's now do 52, right? So let's take a break, right? So shall we start at around 3:10? Right, I will start around at 3:10. Okay.
Sir, sir, are you there? Sir, can you hear me? Sir, are you there? Maggie, can you hear me?
Yeah, I can hear you.
Okay, okay.
Okay, so shall we start? Right. So now I like to introduce you this the concept of the simulation. So let's start talking about that one. So this is the in terms of the simulation. So we are talking about this the concept of the Monte Carlo. So this the Monte Carlo simulations. So the this concept was introduced. Actually, this name comes in as the I think this concept was introduced at the place called the Monte Carlo. So that's why this name came into this particular technique. So let's see that like what's the concept behind this Monte Carlo simulations and so on, right? So now this is kind of like a the another approximation technique. So, in terms of like now, if you're thinking about the different approximation techniques, so we have that the numerically we can approximate things like if you're using the mathematical techniques. So we have that the numerical methods we can apply. So that is the like if you look at the Newton-Raphson method and then bisection method and so on. And so there are like the different the approximation techniques that are available numerically, right? So those are like based on the integrations and differentiations and so on. And so and in that case, of course, if you go further on into that one numerically, we are solving the differential equations and we are using that finite elements and finite difference techniques and so on. And so there are like different numerical approximation techniques that are available, right? So now in terms of the those techniques, uh, if you think about like by involving the statistical concepts and the probability concepts, right? How can we approximate the certain measurements, right? So we can think of like the different approaches we can have there. So in that case, this the people, the statisticians came out with one nice technique that's involved like we are going to learn today. That is the doing the approximations using the random numbers, of course. So we are basically the dealing with the random number. So this entire technique is going to deal with the random numbers. So what are these random numbers? So once it comes to the random numbers, we can identify that these random numbers are the numbers generated from the uniform distribution. So we can define a probability distribution called the uniform distribution. Right? So what is this uniform distribution? So we learn about that. Some of the distributions, that is the normal distribution, Poisson, binomial, and so on. And we learn about several distributions, right? So like that, one of the continuous distributions we can have is the uniform distribution. So that's indicating. So if you look at the random variable and the probability, so we are having the probability as a constant value, right? And that random variable takes value between 0 and 1, right? And then the so that the it is having the probability, we can define it as the um, 0 to any number as well, right? So I can define it between 0 and 1, right? And then the height is also with the 1 here, right? So that's the so we are having that uh, so that random variable can take value between 0 and 1. Know that we can define it between any interval as well, right? And then probability, what we are saying is that it's always going to be the same value, right? And if we can see that, like, we can define this between any two values as well, right? And then probability will be the same height, right? So that height we can define the like that as well, right? So then the uniform distribution you can define between any two values A and B, right? So, but in our case now, when you are generating random numbers, usually we are looking at the uniform distribution between 0 and 1, right? So then what we are saying is that each and every value between 0 and 1 have the equal chance, right? So we are saying that each and every value has the equal chance. Okay, so that's the idea of that. The having the our uniform distribution, and in our Excel, I can use that the RAND command to generate the random numbers. So that's this is always going to give you the random numbers between 0 and 1. Between 0 and 1. Right? So that the RAND command will give you and always a random number between 0 and 1. So then we can convert that to the random number between any other numbers as well. So we have that the option as well. Okay. So therefore the we can use this particular concept of the random numbers, and we can apply this in various areas. So this is the concept that we are going to use in our Monte Carlo simulations, that we are generating the random numbers, right? And then of course now in terms of our computer, so they are going to provide us the random numbers using some inbuilt function there, right? So they always give us the random numbers, and usually we call that as the pseudo random numbers, as we are generating it using a function in our computer, right? So we can identify them as the pseudo random numbers, right? So but anyway, those are can treat as the random numbers, right? So then based on those random numbers, so we can identify that we have the so we are generating the random numbers between 0 and 1, and using those random numbers, we can do some approximations. So our target is to generate do those approximations by using the concept of the random number. So in the earlier days, actually, now you guys are familiar with this number pi, right? So you guys are familiar with this number pi. So we have that number as the 3.14, something like that, right? Now, if you look at that, like this is getting the larger decimal points there, right? So now, if you look at that, the development of this approximation, the value of pi, of course, now I think people have identified. Now, if you look at all these decimal places, they identified up to maybe like 200 decimal places or 300 decimal places and so on, right? So they approximated this value of pi, and so that indicates now we can approximate this value up to the correct certain the digits, right? So of course now there can be like now we can use that our the Monte Carlo simulation technique, as well as the other techniques that we use in the integrations and differentiations and those other approaches as well, numerical approaches, right? So now today I will discuss that how we can approximate it using the concept of the differentiation, the Monte Carlo simulations, right? So so let's see that how we can apply this particular concept here, right? So now once we have that the value of pi, so where it is involved. So if you look at that and practical situations where that this value pi is involved, so that involved in when you're measuring the area of a circle. So we can use that concept, right? So now I can look at that. So if we take the two dimension, right? So I can take x and y plane, right? X and y plane, right? And take in the two dimension, and I can draw a circle like this. So the radius 1, circle with radius 1, right? So it can be like unit, whatever the units, right? So I'm generating as the circle with radius 1, right? So then if I identify the area of the circle, so what is the area of the circle? So that is the pi times r square, and radius, the r is 1, right? So therefore it is pi times 1 square, that is pi, right? So therefore the if you look at this particular circle here, right? So the area of this circle is exactly the value of pi. So that's what we need. Okay. So then if I want to use the random numbers, right? So now my target is to using the random numbers measuring this area, right? So our concept is that. So to measure that, right? So using the random numbers, what I'm going to do is I will draw a square like this. So I will draw a square. So I will draw a square like that. Okay. So then I know that the length of this square is 2, right? So I'm having the length of the square as the 2, right? So therefore I can have the area of the square equals 4, right? So it is 2 times 2, that is 4, right? So area of the square is going to be 4, right? So then the if you take the uh, area of the square, right? And then if you take the area of the circle, right? And if you take the ratios, right? So if I take the uh, area of the circle divide by area of square. So if I take the ratio of these two, what will I get? So that's going to be the pi divided by 4. So if I take the ratio of these two, I'm getting a value of pi over 4. Now using the random numbers, can I get some approximation for this one? And so then that is an approximation for this guy as well, right? So then my target is to, if I want to measure the value of pi, right? So that's going to be equal to the 4 times area of circle divided by area of a square, right? So that is the concept I can use to approximate the pi, right? So then the now if I take this one here, right? So what these decisions suggest that in the Monte Carlo simulations, right? So that this particular concept is that now we can consider that each and every point here, right? So equally distributed, right? So that entire area, we can say that equally distributed, right? And then if I generate random numbers, right, inside this square, right? I'm going to generate random numbers inside that square, right? So then what happens? So then I'm getting random numbers equally inside the square, so inside the circle as well as outside. So then if I take the count of those random numbers that are inside this the square, so inside the circle and divide by the total, so that is an approximation for this particular ratio, right? So that is going to be the concept, right? So we can assume that these are equally distributed, right? So then we can say that they are coming from the uniform distribution, and I'm generating random numbers, right? Between now, I can see that like in terms of that my notation, say I can go from -1 up to +1, right? And then here also it is from -1 up to +1, right? So that means, so I can just take a square like this, right? And that is between -1 and +1, right? And -1 and +1, right? So I can generate the random numbers, right? The between -1 and +1, right? So initially now I say that like if you use the rand command, right? That's going to give you the between 0 and 1, right? So I have that number between 0 and 1, right? I can convert that to the -1 and 1, right? So I will convert that to a random number between -1 and 1. And so I will talk about that, right? How we can convert that to the random number between -1 and 1, right? And then what I need to do is like to represent that x-axis, I need to generate a random number. And to represent my y-axis, I need to generate another random number. So basically I need two random numbers, right? So two independent random numbers, so that is the R1 and R2, right? So I'm taking the two random numbers as a pair like that. Then that pair will represent each and every point on here, right? So I can keep on generating them, say, very large number of times, right? So that's like 1 million times or 100 million times or something like that, right? So that's you can go for very large number of times, right? From 1 billion, 10 billion, something like that, right? You can go for very large number of simulations. That's called the simulation. So you are repeating the same thing, but you are generating the random numbers, right? And what you do is that once you generate a random number, so you have this circle, right? And once you generate the random number, you check whether it is inside the circle or outside the circle, and you put the count, right? So we are just generating the random number. That means random number pair like this, right? So and then we're checking it whether it is inside the circle or outside the circle. And then you are increasing your count. So if you keep on doing that, then eventually you are getting the number of random numbers inside here, right? And then number outside the So then if you divide that total number inside by the total number of random numbers you generated, then that gives you the approximation of pi over 4. And you can multiply it by 4 and you have an estimate for the pi. Everybody see that? So that's the concept of this, the Monte Carlo simulations. So let me show that, right? So that particular calculation in terms of Excel, right? So let me have this Excel file here. So now I have another example here. I will come to this example, right? The before that, I will show you that this the random number concept here, right? So I will write down that so that is my random number 1 and then random number 2, right? So I have the two random numbers representing this one, right? So R1 and R2, right? So let me generate them. Okay, I need to show that like, so if I just use the RAND command, that is going to give me this random number between the negative sorry 0 and 1, right? So the I think yeah, so yeah, so it's going to give me the random number between the negative 1, the 0 and 1, right? So therefore, if I want to convert that to the random number between negative 1 and 1, right? So if I draw the line here, right? 0 and 1, and then negative 1 and 1, right? So I have to expand this to the this interval here, right? So that means like, so this one has a width of 2, right? So therefore, whatever the random number, right? So I'm getting here, so I have to multiply by 2, right? So to increase the width, right? So but if you multiply them by 2, then it is getting between 0 and 2, right? So if you multiply by 2, right? If you multiply by 2, then it is between 2 and 0, right? And the 0 and 2, and 0 and 2, right? So and then you want to shift it back to the negative 1 and 1. So I have to subtract 1, right? So if you subtract 1, then it's going to go back to the negative 1, right? So you can shift it like that. So therefore, I can take this here, right? So that means I can multiply by 2, right? And then subtract 1. So I'm getting the random numbers like that. So same thing I can do over here. And then I can generate them. So I can do this for a very large number of times. So let me do it some number like this, say 1,000 times. So I did it for the 1,000 times, right? So just for the simplicity, I do it for the 1,000 times, but practically you can do this for the 10,000 or 1,000,000, find a very large number of times. Okay, so that's my generation of the two random numbers, right? So you can see some of them are positive and some of them are negative, right? So that's indication of I'm getting that between this entire region. So I want to confirm that whether it is inside this circle or outside. So how do we confirm that? So we can use the formula. We can use to measure the radius of a circle. Right, so that's I think same formula we used earlier as the our distance formula. Right, so we need to measure this distance. Right, so from center up to the radius. Right, so we need to measure that distance. Right, and if that distance is larger than 1, right, so then it is outside. If it is less than 1, it is inside. Right, so we can use that command. Right, so that means, so to check it, right, I can measure that the distance, right? So that is the distance is the radius actually, right? You can measure that distance. No, I'll label it as d actually, right? Distance I can label it as a d, right? So then distance from any point, right, up to the center, right? So I can measure the distance from any point up to the center, right? So I can measure that distance equals to the any point means that our random number, right? So I can take the first random number and then subtract the center. So now in this case, center is 0, right? So we have the center and then second one and subtract center and square the length, take the square root. So it's basically R1 square plus R2 square root. So if you're using different centers, you can change the center, right? So that's, you can define it like that. So I can use that distance command, right? So this is the distance, right? So I can use it. Okay, before that, I have used the square root. So let me take the square root of this one square plus this one square. So that is my distance. So I can do this for the all the 1,000 here, and I have 1,000 observations, right? So, and then the now I have these distances. Now I have can see that like some of them are below 1 and some of them are above 1, right? So I can use that the if then command here, right? And see whether it is inside or outside, right? So that is the checking that we can have, right? So we will check the condition, right? So that's, I can use the if command here, right? So what I want to do is check this one, and if it is less than or equal to 1, right? So if it is inside, I can say output 1, and otherwise I can output 0, right? So what I'm saying is that if the distance is below 1, then I'm outputting as the 1 there, right? And if the distance is above 1, I'm outputting 0, right? So that's, I'm using less than or equal, right? So if it is less than or equal, then I'm outputting as 1 there, and so that means it's a correct one. Otherwise, I'm putting 0 as an incorrect one, right? So I need all the numbers inside, right? So therefore, I'm putting it as it is a correct one or wrong one, right? So I put that, and you can see, so this is 1. So I can get the numbers like that. So you can see some of them are 0 and some of them are 1. So that's how I can get the count, like the in terms of that whether it is inside or not. So 0 means it is not inside. So then I can take basically the summation, right? So I'll take the, so we can take the summation, right? So I can take sum from this one up to the 1001. So I can take that summation as the 793. Once I have the summation as the 793, right? So then my approximation, I can have my approximation. So that's going to be the, now I can use this formula here, right? So now that is the summation is the, now what I have is that, so 4 times so count inside the circle divide by the total, total simulations. So in my example, I did the 10,000, sorry, 1,000 simulations, right? So therefore, you can multiply this number and divide by the 1,000. So I can see that I'm getting the approximation as the 3.17, right? So that is kind of like the correct up to only one decimal place, right? So it's 3.14, right? So if I press F9 again, you can see 3.0 and 3.2, 3.0, 3.16, and so on, right? So there you can see the so different values we are getting like that. So that is now coming only from the 1,000 simulations, right? So easily you can increase this number and you will see how good the approximations are, right? So now, of course, you can do the same thing in terms of the R software as well, right? So I can quickly show you that some R coding on that one as well. So just to give you the idea about that, the random numbers, right? So of course, I will take a new one here. So I think I can go with that. The, so I will define that x as the so I forgot the command for the random numbers actually. It is the no. There is our norms that is from the normal distribution actually, right? So now so I can just search and see, right? So the so that is the run, right? So that's I was looking for the command in the so So I can I can give that the run if command, right? So that in the run if command, uh, it allows me to generate that any number of random numbers, right? And then I can give the range of that side. So I can give that. Uh, so I will first generate one random number. So I will generate it like that. Yeah, so I can generate it X like that. And I can use the same command for the Y. So I have the two random numbers X and Y like that, right? So, and then of course, I will go over here, and so then I can go with that some uh, for loop or something like that, right? So I can go with uh, for loop. It is I had to check on that. I forgot for loop as well. So mm, let me see. Okay, so this is the range. So I wonderful, right? So that's so I can go with that. I can go with some for loop. Mm, so I can do this now for 100,000 times. So like more than that, right? So I can increase that number. So so I can repeat that in the uh, so I can measure that distance here as the D. That is the square root of so I can measure the distance like that. The and then of course I think I can go with that. Uh, so mm, I was taking that I can use that if command here. I think if in the so let me find that if command here. Okay, so I can use this here, right? So it is So I can do some measurement like that, right? So let me run this and see. Okay, I didn't mention that. No mistake. Okay, I forgot something here, right? So I think what I can do is something like this. Let me do something like this here, right? So I can have I'll define some variable as m here, and I can put that as the 10,000 or 100,000, right? And then I can put that m here. So that means now I'm asking them to generate that the x as a 100,000 observations and y as the 100,000 observations. So then I can do this here also. I can go up to the n here, right? And then here that when I'm using it, so I had to put the I here. And so otherwise I'm not using I there, right? So that's what I'm missing there, I think. Okay, so now I think it is running. Yeah. So and then finally I can output my approximation, right? So I can use it as the uh, count multiply by 4 and divide by n. So that is the approximation. You can see that 3.14. Sorry. Okay, sorry. So uh, so now that's so this is the indication of that, like, so we can do this uh, in R, like for a very large number of simulations. So just I can change that number of simulations by increasing the number there, right? So you can see that is generating the random numbers there. And then you can see that 3.144 and so on. And so that's, I don't know what is the actually value of pi, right? So I can even find it here and so and see how good it is, right? The, so you can see that like 3.14159 and so on. And so that's the approximation. I think now people have done it uh, almost like the I think it is computed over 100 trillion digits, right? So it's like they're getting like the larger and larger, right? So as the computation power increases, right? So you can see if you have a much the better computer, then you can increase this number to a very large number, right? So then it's going to give you the very good approximation, right? So we can try to increase another number digit and see. So you can see that like it takes some time, right? So now 3.140, right? So that's still not correct, right? So that we need to increase that number of simulations so that the as it is getting larger and larger, that the approximations are getting more accurate. Okay, so now that is the our concept of the simulations that we can use in terms of the our. So let me close this one. In terms of the approximating the uh, certain values now that we can use this concept on different places, right? So not just now, the later on we are going to discuss that now this concept we can apply on the in terms of the approximating the using the uniform distribution, and not only that, we can use the normal distribution and other distributions as well. So we here we just generated the random numbers. So that is the now we are by assuming that. So we take that like some intervals A to B, and then we are assuming that all these numbers between A and B have the same probability. So that is why we say that is uniform distribution. But sometimes we can see that some of them might be having different probabilities, right? So then we can say that from A to B, right? So they might have different probabilities. So then if you generate, then you can see you're getting more values here, right? And then less values over there, right? So we can use some other distributions to generate random numbers as well. So I'll show you that like we can use other distributions as well, right? And then now today I'm planning to go through like this particular calculation here, right? So that is this one here. So that is to now in terms of like applying this the our simulation concepts, right? We can apply the simulation concepts in different areas. So now I like to discuss that how we can apply this in terms of deciding the some measurements in the queues, and so that's now in our the basic the real world situations, you will see that many places that you have to wait in queues. So that therefore, like whenever you are studying the queue, right? So you will see that like there are the applications that you can have. You can identify that our waiting time in the queue might be very large and so on, right? So we can see some properties like that, and and sometimes that may be like very bad experience for us and so on. And so therefore there are situations that we might have to be in the queues and so on. And so therefore uh, before practically applying it, if you can identify that what are the modifications we can do on queues and so on. And so if you think about those things, then the the uh, so if you can simulate the queue and see that what's practically happening there, and so then that will allow you to identify the various the disadvantages available there and so on. And so we will identify certain properties like that, right? So therefore our now our target is to study the behavior of a queue. right? So let's try to study that one. So now, first of all, let me introduce you in general what is a queue, right? So So if you think about the queuing theory, right? So that's now whenever you are describing a queue, right? The so the important topics that we have to follow in a queue, right? So that is the inter-arrival times. So that is the now whenever you look at the certain queue, like now you can see that like in practical, right? If you go to the supermarkets and banks and any government offices and so on and so there, you have to wait in queues in many situations. So then the main thing that is going to affect on the queue is that as the people are entering the queue, right? So that's always the in real world situations now queuing is kind of like usually dealing with the human beings, but this can apply on many other places as well. Like now in terms of like computer applications, you can see that and sometimes people are submitting jobs to the queue and even jobs to the servers and so on. And so then it is kind of like at the server there's a queue, and so that many jobs comes in and then so we have to identify the length of that queue and so on, right? So we can identify them, right? So that's again a queue, right? So but in our cases, usually you can see that in our companies and so on and so people have to wait in queues, right? So especially banks and supermarkets and the places like that, right? So therefore, the now as the managers and the executive people in that companies and so on, and so you like to manage the queue, so you cannot minimize it. Like you cannot make it zero, of course, right? So that so if you don't have if you make it zero, that means again that is a waste of resources as well. So we want to manage the queue. So we can see that like if the customers are satisfying with like having 2 or 3 people in front of them, then it's okay, right? But if there are like 10 or 20 people in front of you, then people might not be that much happy, right? So that they're looking at how long it will take them to have the service, right? So that's so therefore the so that in the queuing system we need to be careful on, right? So now you can say the practically we like to look at the situation and then now of course we can gather the data, right? And then like by going through that the place, say for example now we can take supermarket and then you can count, right? So within that the some time period, right? How many people entered, and then you can record down their number of people entering, right? So that way you can define that inter-arrival times. You can identify the inter-arrival times. And then in general, what happens is that this inter-arrival times, that's going to be random, right? So that's the having some random pattern, right? So that's it's not always going to be say hello following some particular pattern, right? So that means inter-arrival times will have a certain distribution, right? So we can identify the inter-arrival time distribution. It can be like some common distribution, or we can identify that certain situation and identify their distribution as well, right? So so that is the first thing that we have to identify whenever you are looking at a queue. And then the next thing is that we have the service time. So that's again some random variable, right? So now, for an example, if you go to the bank, then people might have different the tasks that they have to do, right? So then each person will take different time to resolve resolve that problem, right? So they having different time slots, the different time period to resolve their work. So therefore, our service time also going to be a random variable. Right? So we can identify these two are the two main random variables whenever you are looking at a queue. Okay. So then we can see that we can identify the distribution of these two random variables. Right? So now our target is that now we can use some common distributions as well, right? So we'll come to that later, right? I will show you that how we can use some common distributions there. But of course, now with the common distributions, what happens is that the there are theoretical measurements that we already have. But when it comes to the other distributions, right, some unknown situations, right? So then the theoretical background is not there. So that's why we need the simulation. So now, in terms of that, once you identify in the queue, right, so what are the things we like to measure, right? So now these are the two variables, right? So using these two variables, we like to measure that our average waiting time. So it can be like waiting time in the queue or waiting time in the system, right? And then we can measure that the average length of the queue, right? Or average length in the system, right? And so on, right? So therefore, like we can measure the different measurements like that. So our target is to measure those things using our simulations. So we can estimate them. As you can increase the number of simulations, those estimates are getting better and better. So that's what we are trying to plan here. Okay, so and we can see that like this simulations concept we can apply on different areas, right? So we'll see that like I'll show you that several other areas we can apply that simulation concept as well, right? So this is one area that we can apply. And in general, of course, now the simulations can apply on many areas. So this kind of very useful technique, and you will see that even if you are doing some research and so on, and so even there also you can apply, right? When we do some our research and when we identify like new techniques and so on, and so then again, what we do is like we can do the simulations and they see that like whether our theoretical result we are getting is correct or wrong and so on, and so we can do simulations and see whether we are approaching the same thing and so on. And so once you get that some theoretical results, we can do the simulations as well. So those are the different approaches we can have, right? So now this is now in terms of that the queuing theory, right? So we have that these two are the two main variables that we can have, right? And then our measurements. So our measurements that we like to have. So in general, I can define as the average average length of the queue, right? And then the average waiting time, queue, and so on, right? So we can define some measurements like that. So we'll come to this, right? So we can define this average length and average waiting time and so on. And so we can measure those measurements there. And that will give us some idea, right? So whether that our customer will be satisfied or not, right? And then we can see what are the modifications we can try and so on, right? So let's look at that now. These are the cases we're going to have, and let's the look at one of those examples I have here, right? So now let's see that now the very simple situation. Now we have like the medical center, so it has only one doctor and one nurse. So like the practically this will be like much more complicated than this, right? So now to model this one simply, right? I'm going to define a medical center that has only one doctor and one nurse. And then what we do is like now, as the people comes in, right? So first they are going to check by the nurse, and then they're going to check by the doctor. So what happens is now once they come in, right? So once people come in, right? So they have to first the so they come in, right? Once the person comes in, right? First they have to meet the nurse, right? And then they're going to go to a now they come in and they join the queue, right? So they as people are coming in, right? So they're going to join in a queue here, right? Right, and then they meet the nurse, and then they will be in another queue, right? And then they will meet the doctor, and they go, right? So basically now you can see they will have two queues here, right? So so that's the our very simple situation. Now we can see that like very simple situation is kind of like having only you're coming in and meet the doctor and go out, right? So that's the most simple situation you can have, right? So this kind of like one step ahead of that, right? So we can see, so they are going to come in, right? The so they have to wait in both places, right? And then service done, priorities in the first come first serve, right? First in first out, right? So that's usually the procedure, right? So if you change that, of course that's a different issue. So you have to be careful on that if you're going to change in that one, right? So therefore practically we are saying that like we always serve first come first out, right? So so then we are having that service rate, and then of course now the to make it simple, of course, right? So service time for the nurse is we are saying that it's always 7 minutes, right? So it can also be a random number as well, and so it can vary as well. So for the simplicity, I'm taking as the 7 here, and later on I can change this one to the random number as well and see what are the modifications we can get, right? So and the and then service time of the doctor is a random number, right? Uh, and then the time between the arrivals and the service time of the doctor, right? So they are given in these two tables here, right? And then the using simulations to determine the average time the patient spend in the doctor's office, right? So the from the arrival to the leaving, right? So we want to measure that one, right? So those are the things that we want to measure there, right? So the so now if you look at the time between arrivals, so that is the arrival and the inter-arrival time or the time between arrivals, right? And the that's the inter-arrival time, right? And we are saying that now by doing some research or like some survey, whatever, right? So they have some distribution there, right? So this is the distribution they are providing on that, right? So they are saying that uh, there will be like every 5 minutes, right? So then people will arrive with a probability of 0.5, and then every 10 minutes people will arrive with a probability of 0.3, and 15 minutes probability with 0.2, right? So so that means like so usually within 5 minutes, right, you will see a new patient, right? So that's 50% of the time. Within 5 minutes, you will see the patient, and then and there might be like 30% of the time their gap will be 10 minutes, and the 20% of the time gap will be 15 minutes, right? So that's the measurement that you have normally, right? And then of course, we can have the cumulative distribution here, right? So we need only that, the cumulative distribution, the lower limit here, right? So from 0.5 and 0.8, right? So these are the lower limits and these are the upper limits of the cumulative distribution, right? And then same thing as the doctor's service time, right? So 4, 8, and 12, right? So that take 4 minutes and 8 minutes and 12 minutes, right? So the 30% of the time doctor will take 4 minutes, and 50% of the time doctor will take 8 minutes, and very rarely he will take 12 minutes as well, right? So that's the service time of the doctor, right? So this information is available to us, and then from there, right, I can calculate these upper limits and the lower limits, right? So that's the cumulative distribution. CD is indicating the cumulative distribution. So that's taking summation of this, right? So 0.3, some plus 0.5, and then everything is 1, right? So in the lower limit, I think was 0, and then 0.3, and then 0.3 plus 0.5, right? So that's, they have these two numbers there. Then of course now later on in these calculations, I'm going to use that uh, the uh, the lower limits here. I will use them, right? So then now I did the simulation for the 45 customers here, right? So there you can increase that number, right? So just we need to first identify what are the things we need here, right? So customer number is here, and then I'm taking my random number one, and so I'm just using that the RAND command, right? I'm generating the random number. In general, of course, now if I generate the random number, that will become like a very small number, zero point 0. Like, so that's going to give us some larger number of decimal places. So that's why I'm using this trunc command as the truncating, right? And using only two decimal places, right? So even you can use it without that command as well. Yeah, so to see that, like, to see these probabilities, these are now the probabilities, of course, right? The random numbers between 0 and 1, so they are kind of like representing a probability. So I'm having these probabilities, and then I'm having these random numbers to indicate this inter-arrival time. IAT is indicating the inter-arrival time, right? So let me write down some of those. And then AT is the actual arrival time. Okay, so these are the uh, commands. So these variables I'm defining here, and then what happens is that, so now I'm generating these random numbers, and these as they are between 0 and 1, then I can compare that with these probabilities here, right? So what I'm saying is that, so if I have this 0.66, so that falls under this category here, 0.5 to 0.8. So that means I'm having the patient, the first customer comes in at the time point 10. And even I can take first customer arrivals at the 0 as well, right? So, but here I'm taking it as the first one came at the number 10, a time point at 10, right? So, and therefore, I can take the arrival time of the first customer as the time point 10, right? So I'm starting my calculation from the time point 10. Okay, so that means the so you can see that, like, so these are like all these are, now I'm looking at on here, right? So which interval they are going to follow, right? So that I can use this lookup command, right? So I'm saying that lookup, looking at this value here, right? And then check the this column here, right? So, and then if this number is like this number is above any of these numbers, right? So then it falls under that category, right? So if it is above 0 but below zero point 0.5, then it goes under this category. And if it is above 0.5 and below 0.8, it goes under this category, right? So therefore, if it is fallen under that the category, then I'm asking them to use these numbers and put it here. So that is what your lookup command is doing, right? So therefore, I'm getting these interarrival times, and then I'm just adding those interarrival times into the previous one. So therefore, this is kind of like keep on increasing, right? So arrival time is always keep on increasing. So that's the arrival time of the patient, right? So this is regarding the patient, right? So that's this information is regarding the patient, right? Up to this point. And then this is the thing that we have with the nurse. So now you are joining the queue here, right? And then you have to look at the nurse and see whether that nurse is free or nurse is engaged with the customer. So then first one, you don't have to do anything, right? So because that's the nurse is already free, right? So therefore, that's a first customer, right? So therefore, this is equal to this one, right? And then service time of the nurse is, we are saying it is 7 always, right? So but again, now we can do that as the random number here, right? And later on I will do that, right? So we can put a random number here as well. So then the so that the service time is 7. And so the first one now in this case, now the every time when I run it, these numbers are changing, right? So now it becomes 15 here, right? So first one came at the time point 15, and then they get the service and it is done at 22. Okay, so that's the information I have. So therefore, the so just the summation of these two, right? And then I can calculate the waiting time, right? So the waiting time is the difference between these two actually. So I can define that waiting time here, and so now even I can apply that same thing over here, right? So here also I put the same thing, right? So it's yeah. So the waiting time, right? So I can define it as uh, the arrival time and the start time, the difference between these two, right? So you can see arrive at 15, but start at 17. So the difference between those two will become the waiting time here. So now for the nurse, now we can calculate that information, right? So now if you look at here, right? So now the second customer, right? So now the first one came at 10, right? And then the finished the work from the nurse at number time point 17. But the second one came in at the 15. So therefore, to start the work for the first one, he has to wait until this one, right? So therefore, the now the start time of the first one has to be the maximum of these two. So always the start time will become the maximum of these two, right? So that's why I have this formula here. That's the maximum of the finish time of the nurse and the arrival time of the patient. And so that's these actual times, right? So therefore, the maximum of those two will put as the start time. And then uh, so then you can see that difference will give you the waiting time of the patient. So these are the waiting times on the at the nurse, right? So you can see sometimes they has to wait and sometimes they don't have, right? And then there's like larger waiting times as well. So you can do this calculation, right? So that's a larger calculation. So you can perform like that. So that's regarding the nurse, right? So then I can go to the calculation at the doctor, right? So then we can they start the calculations at the doctor's office, right? So then now we have the start time at the doctor, right? So what is going to be the start time at the doctor? So now for the first customer, that is exactly the finish time of the nurse. So whenever they finish at the nurse, they can go to the doctor. So I can put these two as the same thing, right? And then I'm having the random number again here, right? So that's again using the same command. And then based on that, I use the lookup command, right? And then I'm checking that these probabilities here, right? And then finding out these numbers. Yeah, so it is 8, 4, 12, and so on, right? So now they can have like this distribution can be very large, right? So that it doesn't matter. Just you can check it there, right? So that's how usual now. These are like for the simplicity, I'm having that something like this, but practically this will become much larger distribution than this one, right? So I'm having very simple one here. So now we have the first customer that service time is 8. So therefore, at the doctor's office, doctor will finish at the time point 25. So that is the summation of start time and the uh, service time. Right? So ST is indicating the service time. Right. So that is now just to indicate that the WT is indicating the waiting time, right? And then the ST is indicating the service time, right? So yeah, so those are the commands we have there, right? So then first customer will finish entire work at the time point 25, right? And then first customer will always not have any waiting, so that is 0, right? So that is the first customers and the so that first customer came in at time point 10 and goes out at the time point 25. So that means first customer in the service time as the 15 minutes. And the first one will stay in the system for 15 minutes. Okay. And then the second one, now you can see that second one will finish at the nurse at the time point 24, right? But then the uh, first one will finish at the time point 25. So therefore, you have to wait 1 minute, right? So until the first one is done, right? So therefore, you can see the start time, you can use again the maximum of these two, right? So that's how we can calculate them. So these are always going to be the maximum of these two, right? And then the difference between these two will give you the waiting time. Now this is the waiting time at the doctor's office, right? So there are like, so the two places, so two waiting times are there. And then for each patient, the taking the finish time and subtracting the arrival time will give you the time they spend in the system. So like that, now we can repeat this for several customers. So finally, so I did it for 45 of them, but you can keep on increasing this, right? And then the other question is that determine the average time patients spend in the doctor's office, right? So that is the so that means from the arrival to the leaving, right? So that's for the entire time. Now we can find out that average time spent in the doctor as well as, but that's already we have that service time, right? So that we know, right? So that for the entire queue, so what is going to be the average waiting time? So let's see that. So there is this one. So then you can take this average. Also, so you can see that the average waiting time, the average time they're spending in the system is out of 45 customers here, right? So that's 21.3 minutes, right? So once the patient enter there, once the patient enter there, right? So before, like after meeting the doctor on leaving, so they have to spend 21.3 minutes on average. So now practically now you can see that, like, so you can check on these numbers, right? So now you can identify, right? So uh, now you can check with your patients and see whether they are happy with this number or they want to reduce this number, right? Of course, they will not ask you to increase this number, right? So it's always whether you want to reduce this number, right? So now if the patients are not happy with this number, right? So 21.3, right? So now if I press the F9 again, right? That number changes, right? 17, 20, 18, and so on, right? So that's kind of like it's around 18, right? So it's if you keep on changing it, right? So it's varying a little bit, right? But it's around the 18, right? So and you can see that, like, I can increase this here, say up to, I'll go up to 100 here. So I will just increase this. Maybe I can select all this together. I forgot. Yeah, I can do it that way, right? So, and then this is the, so then I can see that average is around 20, right? So it's the on average, the time is going to be 20. Oh no, that's changing, right? So it's now, as we are increasing the number of patients, I don't know whether I change anything here. So you can see that, like, as we are doing like larger number of simulations, So it's getting a bit more varying, right? So that's these times are getting much more varying. So you can see it's better to do like larger number of simulations, right? So then you can see how it is varying. Okay. So, and of course now this is kind of like this might be varying because now you can see this distribution is also kind of like the much wider distribution, right? So that's why the this time might be varying that much. Okay. So the so now of course now the we can try to do some modifications, and of course now I can change that to the uh, service time of the nurse here, right? I can change that and see, right? So if I include the random number for that one as well, right? So what are the changes we can observe and so on, right? I can discuss on that, right? So before going into that, the now uh, if you think that now the this average value here, right? So now what we can do is like you can run this average on several times, right? And then the you can take the average of all those averages as well. So that will give us much better idea, right? Now, once you're looking at that number, if the patients are not satisfying with that, and so they want to have a much smaller number, what are the modifications you can try? So in terms of that, the modifications here, right? So now one thing is that now we have just one nurse and one doctor. So that means the modification, one thing you can do is that we can increase the number of number of nurses, right? So that's so since we have only one nurse there, right? So that they are taking 7 minutes. So that person is taking 7 minutes, right? So if you put that two nurses there, then this will be the different number there, right? So that's it's going to change, right? So that service time will change, right? And then if you put two doctors there, then that service time is also going to be changing, right? So like that, we can try some modifications there. So later on, we can think of like the other modifications. We can go like that. Okay, so that will allow you to the identify the various changes we can identify there. Of course, now in terms of these queues, always we can identify that as you're increasing the number of servers, these are the measurements are getting smaller and smaller. And so these, if you want to reduce that, means better thing is that so you increase this number of servers. Of course, now there's no point of increasing number of doctors without increasing the number of nurses, right? So because that number of nurses, they are taking 7 minutes, right? So that they, without changing that number, then if you increase the doctors, then the doctors might be more idle. So we can, the one additional thing we can calculate here is the idle time of the nurse and the idle time of the doctor as well. So it is the opposite of the waiting time, right? So that's the idle time of the doctor and the idle time of the nurse. So we can calculate that as well. So I'll bring that next time, right? I will bring those calculations here, right? So, and what we want to make sure is that the idle time has to be also the smaller as well, right? If you're having that like the much larger idle time, that's also kind of like indicating the uh, they are like wasting their time, right? So it's they don't have much larger queue. So that in that place, like if you have like two nurses, then that might not be the necessary, right? So that one nurse is enough. And usually in practice, of course, that service time of the nurse will not be same number, right? It's also random, right? So we can change that, and we can do some modifications to that as well, right? So So those are the other changes we can apply here. So right now, before going into that, now what are the other calculations we can have here? Right now we have that waiting times here. So we can take a look at the average waiting time as well, right? So this is the so that is the average time in the system, right? So then the so we can calculate the average waiting time, and that is the at the nurse, right? So that's one measurement, right? So I can take the average, this one here, and then the and doctor, right? So I can measure those two measurements as well, right? So those are the average times we can have at the doctor and then at the nurse, right? So now by looking at those two numbers, it's kind of like they are varying a little bit, right? So that's the those are also varying very rapidly, right? So that's the different numbers are getting there, right? So and then like usually what I can notice is that the average waiting time in the doctor is larger than the average waiting time at the nurse, of course. So that's another thing we can observe there, right? So by looking at these numbers, the average waiting time at the nurse is kind of like smaller to the waiting time at the doctor. So that indicates, of course, now adding that two doctors there might be effective, right? So that the without adding a nurse, right? And you can do the simulation and see like by adding a nurse as well, right? Any changes you can observe there, right? So those are the other things we can observe. Okay, so so like that we can try some modifications, right? So okay, right. So now for the today I will stop it right now. So I will bring those other modifications. So this like the first time I'm teaching this part, right? So I don't have much notes to uh, going beyond that. So I will stop it for the here today. So so next time I will bring like some modifications and so we'll do some modifications on here and so we'll see that like what are the changes you can get and you can try that and so I will upload this file and you can try those as well, right? And then you can do the same thing in R software as well, right? You can run the R coding on this calculation as well, right? So you have those of the applications as well. Now, once the thing is that now if you do this in R software and if you do that for loop or whatever, right, you can see that easily you can run the larger number of simulations. So that will allow you to run very large number of simulations. So this is in Excel, of course, you have freedom to do like I think like I noticed that there are like you can do up to like 10,000 simulations as well, right? So that's also kind of like for the queuing system and so on, and so that's kind of like a good enough, right? So we don't need that much of larger simulations here, but it's better to have the larger number as well. So so that is like the one of the applications that we can have in terms of the simulations, and I will bring few more applications next time. So with that, then I can end up the lecture for the today. And see you guys next week. And okay, I will give you the attendance, and I did not give the attendance. So let me open that one. So, so so you can mark your attendance, and once you're done, you can leave as well. And if you have any questions, you can feel free to ask. And hope you guys are done with the assignments, right? If you have any doubts or any questions, let me know.
Excuse me, sir.
Yes, yeah, go ahead.
Sir, is it possible to extend the assignment dates a little bit?
Okay, yeah, I can extend it by 1 week, right?
Thank you very
Yeah.
much.
Okay, I will extend it. Yeah.
Excuse me, sir.
Yes, yeah, go ahead.
Sir, also, is it possible to do some model papers? And also, do we have to do R in the exam also?
No, in terms of R, I will not ask you to do any R coding at the exam. I will give
Yeah.
you some outputs you can get from the R, and I will ask you to interpret them, something like that.
Okay.
Right? So it will be difficult to ask you to run the R code actually. So
Yes.
everything we'll do by the Excel.
Okay. If you
Right.
can do some model papers, that would be great, sir.
Yeah, yeah, I can do some model questions. Yeah.
Yeah. Thank you, sir.
So how long we have? Like, so how many weeks we have more?
I think as
Do
per
you-
the schedule, by the end of February, we have to finish the lectures.
Okay, so that means like, so today is the 7th, right? So it is until 28th we have the lectures. So one, two, three more lectures, right? Is it
Yeah. Yeah.
3 or 2? And I don't know. I will check and see, right? So
Thank you, sir.
yeah, okay.